Okay, I wanted to do some exercises from section 8.3, and here we have a permutation. This is in cycle notation. And the idea of cycle notation is that the element that an element goes to is next to the element. So here you have 1 goes to 5, 5 goes to 2, 2 goes to 6, etc. So if I was going to do part A, usually when you write a tableau, you list all the elements in order. Now here it says 1 goes to 5, 5 goes to 2, 2 goes to 6, 6 goes to 3, 3 goes to 4, 4 goes to 1. That's how you do it. All right. Now for B, if you look at figure 8.3.1, it's just an arrow diagram. The easiest way to do this is to write this as a cycle. 1 goes to 5, goes to 2, goes to 6, goes to 3, goes to 4. So you can just write it like this. Now later on we flatten these just to make things nicer. So I think we do something like this. 1 goes to 5, goes to 2, goes to 3, goes to 6. Oh, sorry, did that wrong. 2 goes to 6, goes to, well, 3 goes to 4, goes to 1, right? Now you can put them in any shape. The important thing is that they do cycle around, right? So that's enough for that one there. Okay, let's look at the next one. The next one says write this permutation in S7 in tableau form. Now the important thing to notice here is that this says S7. Since it's S7, we should have 7 elements in the tableau. So we're going to have 1, 2, 3, 4, 5, 6, 7. 7 elements in the tableau. Now, since this doesn't specify what 1 goes to 1. 2 goes to 4. 4 goes to 3. And 3 goes to 2. We also didn't specify 5, 6, and 7, so we have 5, 6, 7 like that. All right, so that's the answer for part A, and the others are similar. Okay, for next problem is this one, 8.3.12 part A, I was going to do. And let's move it over. Don't need this. All right, so I want to draw a figure similar to 8.3.1. 8.3.1 was the cycle figure, and this is a permutation in S5. Now, when I had the tableau here, I did show all of the elements in the set, even if they weren't moved. But typically, when you do these figures, you don't even show the elements that don't move. For instance, this is S5, 1, 3, and 4 don't even move. So there's no need to even draw them. So you might think, just starting off, if I have 1, 2, 3, 4, 5, like here's 1, 2, 3, 4, 5. Here I have the 2 goes to the 5 and the 5 goes to the 2. It's really not necessary to include the ones that don't move. Don't include the points that don't move. All right, so we can just do it this way. 2 goes to 5 and 5 goes to 2. And that's all. It's actually called a 2 cycle or a transposition, right? And the other ones will be similar. Our next problem, 8.3.17, Part A, we're going to compute composition of permutations in cycle notation. Now this delta sigma, that means the same as delta composed sigma. Right? And we can see where things go one by one. So let's look at these one by one. 1 under sigma doesn't do anything because sigma doesn't even affect 1. Right? And then that 1 under delta goes to 3. Right? What about 2? 2 under, well, let's see. It's better for me to do this in cycle structure. So I see that 1 goes to 3 under delta sigma. So I can, so then what does 3 go to? 3 under sigma goes to 4. Under delta, 4 doesn't go anywhere because delta doesn't even affect the 4. So that goes to 4. All right, so what does 4 go to? 4 under sigma goes to 7. And under delta, the 7 doesn't go anywhere because delta doesn't even include 7. Right. So let's just keep on going merrily along. So let's see where 7 goes. 7 under sigma goes to 3. And 3 under delta goes to 5. All right, so let's do 5. 5 under sigma goes nowhere, goes to 5. And then 5 under delta goes to 1. Okay. Now if I try to do 1 again, I just go back here and I get 3, 4, 5, 7, 1. All right. So here we have a cycle. 1 goes to 3, goes to 4, goes to 7, goes to 5. I don't need to write the 1 again because if I close it off like this, that indicates that this is a cycle. All right. Now, we haven't included 2, and we haven't included 6. Okay. Where does 2 go? Well, sigma doesn't affect 2, and delta doesn't affect 2. So 2 doesn't go anywhere. I don't even write it. 2 and 6 are not changed. So you don't write them. You just get this cycle that doesn't involve 2 and 6. So you can do all of them that way. Just go through and see where each one goes. Do it in a cyclic way. If 1 goes to 3, then compute where 3 goes to, and so on. Okay, next we convert tableau form to cycle notation. And this is pretty straightforward once you get the hang of it. So just watch what I do here. First of all, 1 goes to 2. Then 2 goes to 1. That means I'm done with that cycle. I'm finished with 1, I'm finished with 2. Now I need to see where 3 goes. 3 goes to 5. 5 goes to 3. So 3 goes to 5. 5 goes to 3 means I close off that cycle. I can't get outside of that cycle. All right, so I've used 1, 2, 3, and 5. The smallest number I haven't used is 4. 4 goes to 6. 6 goes to 4. Close that off. Now I've used all my numbers from 1 to 6. So this is the permutation in cycle notation. So that's the answer right there. All right, so you can see, you can read it off from the tableau without doing any calculation. Okay, next 8.3.33a. Let me compute the product sigma tau. Remember, tau first and then sigma. Right? So let's go ahead and see how this works. I'm going to do this without a diagram. See if you can follow what I'm doing. Now we're going to do this in a cyclic way. So let's see first what 1 goes to. Right. Now, what does tau take 1 to? Well, tau takes 1 to 3. but then sigma takes 3 to 4. So sigma tau takes 1 to 4. All right. Now I want to see what happens with 4. Tau doesn't do anything to 4. Sigma takes 4 to 3. So I have a 3 here. All right, now what does sigma tau do to 3? Tau takes 3 to 7. Sigma takes 7 to 1. Okay? So 3 is going to 1. I close off that cycle. Now I've used 1, 4, and 3. The smallest number I haven't used is 2. Tau takes 2 to 6. Right? Then sigma doesn't do anything to 6. So the net result of sigma tau is 2, 6. All right, what happens to 6? Tau takes 6 to 5. Sigma takes 5 to 7. So in sum, sigma tau takes 6 to 7. What happens to 7? Tau takes 7 to 1. Sigma takes 1 to 2. So that takes 7 to 2. Close that off. All right, so I've taken care of 1, 2, 3, 4. What I haven't done is 5. Now I've used up everything except 5. I should just check that 5 goes to 5. Well, tau takes 5 to 2. Sigma takes 2 to 5. So your answer is just this. Since 5 doesn't move, we don't include it. Right? And you can compute all the products in the same way. Okay, my last problem from section 8.3 is 8.3.37. I want to list the cycle structures of permutations in S6. S6 is the permutation on 6 letters or 6 objects. Now let's take a look at this example 8336 and see what they did. Now when they counted up permutations on S5, they had the identity. Then they looked at single cycles. Then they looked at 2 disjoint cycles. It wasn't possible to have 3 disjoint cycles. So let's take the same approach when we look at S6. We'll look at well, first of all, we certainly have the identity. Then we can look at single cycles. Then we can look at disjoint cycles. And then we can look at more cycles if we can get there. Okay, so S6 has the identity. I can actually type this, I think. Okay, let's see if I can make this bigger. Okay, all right, then has single cycles of length. Now, what's the largest possible cycle you could have? Well, because there are 6 objects, you could have a 6 cycle. 1 goes to 2, goes to 3, goes to 4, goes to 5, goes to 6, goes to 1. So 6 is the largest cycle you could have. But you don't have to include everything in the set in your cycle. So you could have a cycle of length 5. 1 goes to 2, goes to 3, goes to 4, goes to 5. That's a cycle of length 5. Now, there are many cycles of length 5. You could go 5 goes to 4, goes to 3, goes to 2, goes to 1, or some other combination. If you think about it, you could also have cycles of length 4, 3, and 2. All right. Now, how about pairs of cycles? Now, there are several combinations. Suppose one of those cycles has length 2. Then how large could the other cycle be? Well, it could be 4, or it could be 3, or it could be 2. Okay. All right, now suppose it doesn't have any cycles of length 2, but it has cycles of length 3. So if it had one cycle of length 3, it could have another cycle of length 3 because there are 3 more elements left. Now, if I have a cycle of length 4, the only possibility is that the other cycle has length 2, and I've already counted that. So how did I do this? I looked at pairs of cycles, one of which was 2, had length 2. I exhausted all of those, and then I said, well, can I go larger? And yes, I could go larger. I did 3 and 3. So that gives us all pairs of cycles. Now, can I have triple of cycles? I could, yes, I could have 2, 2, 2. I could have 3 2 cycles. Okay, so that's what we have here. We have single cycles of length 5, 4, 3, 2, 6, 5, 4, 3, 2. We could have one cycle of length 2, one of length 4, one cycle of length 2, one of length 3, one of length 2, length 2, length 3, length 3, or I could have 3 different cycles, all of length 2. And those are the only possibilities. Now, for each one of these possibilities, there are a large number of permutations. I can't tell you the numbers exactly, but this one here has maybe over 20 different permutations have this cycle structure. But this gives all the possible cycle structures for permutations in S6.